Good morning, everyone, and thank you for joining us today for our MPS Camera Switch webinar. I'm Melina Dabaca, part of the growth marketing team here at MPS, and I'll be joined today by our technical marketing engineer, Elmedi Haras, and Wilson Fu, the MPS Automotive Product Marketing Manager, both experts in advanced driver assistance systems. Today, we'll learn about how addressing the missing piece in your ADAS architecture, the camera switch, can significantly improve safety, performance, and system efficiency. But before I hand over to our presenter, just a few housekeeping notes. This webinar is being recorded and will be shared with all registrants. It will also be posted on our website within the next couple of days. We will also provide a PDF version of the presentation so you can review afterward. And all of our previous webinars, and this one too, will be available at monolithicpower.com/support/webinars. And as a reminder, attendees are on mute. If you have any questions, please use the Q&A button at the bottom of your Zoom window. And all questions will be answered at the end of the presentation. So with that, I will turn it over to Elmedi. Good morning, Elmedi.
Hi, good morning. Thank you so much, Melina. First, thank you so much, everyone, for joining us for this webinar. And please don't hesitate to ask all your questions. I will really be very happy to address them at the end of the webinar. So this webinar is going to be addressing different challenges into the way that we can enable the agility and the scalability when we are powering our next generation ADAS cameras. And in fact, we can't really talk about the subject without addressing some fundamental concepts around the vehicle itself. And the first subject I would like to start with today is how does the vehicle life cycle looks like? And this is going to be our opening for today's deep dive. Let's start with that. First of all, so the vehicle life cycle refers to the stages a vehicle goes through from its start of production to its end of production. And during this cycle, the vehicle undergo various updates and changes to existing features, as well as the introduction of new features. In fact, at the launch phase, the vehicle is first introduced to the market with a huge focus on initial sales and marketing efforts. And as the vehicle entered the growth phase, minor updates are made to existing features. Then moving forward to the maturity phase, where we see more significant updates, such as the mid-cycle refreshes and the addition of new technologies. And this can be repeated several times as the vehicle program continue until the end of production. These updates are necessary for different reasons, and we may want to include some technology advancement, design refreshes, or just regulatory or compliance updates. For example, we can include new driving assistant or infotainment features. And these features can often be added after the commissioning via an update. Like this, we can keep the vehicle fresh and new and ensuring the best-in-class driving experience. From the figure here, we can say that development and the production of modern vehicle is a very complex process. And to manage this complexity and ensure that the vehicle meets the evolving needs of consumers, automotive manufacturers must adopt a structural approach to system design and architecture. Most common architecture in the modern vehicle are the domain and the zonal. Let's have a look at this. The domain architecture refers to the organization of the vehicle system into distinct domain or areas of functionality. This can include domains such as powertrain, chassis, body, ADAS, telematic, EVI, for example. Within each domain, a range of subsystems and components work together to provide some specific functions and features, following what we call a kitchen sink approach. And while the domain architecture offers many benefits for modern vehicle development, it also presents several challenges and disadvantages, such as increased complexity. In fact, as breaking down the system into the smaller domain, we may introduce new interfaces and interaction that must be managed. Moreover, the limited processing power of individual domains can make it very challenging to scale the system to meet increasing processing demands or handle complex tasks. And since the domain architecture requires communication between the different domains, This also introduced additional latency, which is not absolutely in concordance with the high performance requirement or the strict real-time constraints. The domain architecture can result in tight coupling between domains, making it very challenging to add new domains or modify existing one without affecting the other part of the system. In fact, if you would like to add any other branch here, it's going to be complicated because of all the above we just said. So the limited processing power, the latency issues, which make the domain architecture not open to expansion. So just to summarize, the domain architecture presents these challenges, such as the limited processing power, the low latency communication, and limited possibilities to expansion. From here, we have been thinking, what should we do next? In fact, we did go through a disruptive transition toward the zonal approach to bring answers to those challenges coming from the domain architecture. Let's have a look at those. So the zonal approach is highly scalable by design and by nature. It's open to expansion, upgradable, and can enable a very fast development cycle. The question I had when I did write this sentence regarding the fast development cycle is how does the zonal approach is really allowing that? Well, that question, we're going to try to answer it in the next slide. In fact, the zonal approach is also addressing the ADAS as it's becoming increasingly critical and complex, while we need to address the high flexibility and scalability. The challenge is there only one approach to the zonal through the different OEMs? The answer is no. Different OEMs may adopt a variety of topologies when implementing the zonal architecture. Some OEMs may choose to centralize certain functions or components within a single zone. For example, OEM 1, OEM 3, OEM 4, or OEM 5. While others may distribute them across multiple zones, and also others may just build their zonal around some specific component or subsystem, like the powertrain, the chassis, or the body. Also, others may define the zones based on the functional areas, like the safety, the comfort, the convenience, or just mechanical constraints. Another idea is that some OEMs may adopt more of hierarchical topology, while higher level zones will control the lower level ones, like in a pyramid, while others may just use a flat topology where all zones can operate at the same level. And if we talk specifically on the ADAS, it needs also to be adaptable to those different variety of topologies. Do you remember the question we had before? How can we have the development cycle as fast as possible with the zonal, or how the zone is really enabling this fast development cycle? Let's try to answer that. The zonal architecture is a key concept, again, in the development of the modern vehicles. This is something that we can agree on. Also, the fact that different OEMs may adopt different variety of topologies would definitely change our way of developing a new product. This is very fundamental shift in how vehicles are designed, developed, and operated. And in the traditional development cycle, the hardware and the software were linked together. And after the start of production, update of any function was complicated, challenging, and costly. And as a reminder, we have been using domain architecture here. That wasn't the best approach at the time, with all the challenges that is coming from the domain, the low latency, it's not very expandable, and all the problems coming from that. The new approach is of the development cycle is with the hardware and the software that are no longer linked. So we can launch a vehicle at the start of production, SOP, and continue the software development over a hardware that enables the continuous expansion and improvement. And this is what we call today the software-defined vehicle, aka SDV. Those software-defined vehicles are no longer static entities, but rather a dynamic system that can evolve and adapt to the needs and preferences of their drivers. For example, we may continue fixing bugs, enhance driving experience, enhance safety, or even have just preventive maintenance. In fact, the remote diagnostic and over the air or the OTA update going to reduce the need for physical maintenance and garage visit, and thus improving the driving experience and OEM brand. Let's recap. So we have a new zonal architecture that is reshaping the global electrical architecture and that is answering to challenges such as flexibility, possibility for expansion, and bringing new ideas. These zonals may differ from one OEM to another based on the topology, distributed, flat, or centralized, or just other. And finally, the new development cycle where the hardware and the software are no longer linked. The question is, how can we answer all those new challenges that are coming at the same time for the next ADAS? And the solution is we need to have a highly flexible hardware system that enables the adaptability offered by the software. In the first slide, if you remember, I did give one example of including new driving assistant features. And this can be added through an update, for example, the OTA, the over-the-air update. And I would like to push this example a little bit more, and let's just focus on one today that is main interest for us, which is the cameras, and more specifically, the camera switch. But first, let's see what are the use cases of the camera. The camera can be used at different locations of the vehicle for different purposes, of course. For example, in the middle for the traffic sign recognition, for the lane departed warning, for the emergency braking, for the collision avoidance. On the lateral for the surrounding view as a 360-degree fisheye view, or in the back for the park assistance surrounding view collision. So the camera are used for different important function into the ADAS as driving assistance. And these cameras need to be supplied by a power source. And here where the camera switch come to play. And this camera switch need to satisfy some important functions. And these functions are, first, it need to be scalable. What do we mean by scalable? We need, for example, to be able to address multiple outputs and to scale from one output to 2 to 4 or even more. Moreover, the output itself should be able to drive different level of output current. The current that we're going to need for the surrounding view is not the same one that we're going to need for the rear cameras, and not also the same that we're going to need for the front camera. And this can be, and this change can depend on the camera resolution, the conception, or just simply a request. Second, the camera switch need to be flexible by enabling programmability, configurability, and diagnostics. For example, the output current feedback need to be provided for diagnostic purposes or safety. Input, output, and internal voltage, or just some internal diagnostics to attest that the camera is functioning correctly. And in fact, the camera switch is functioning correctly, and by extension, the camera itself. And like you know, we are also targeting more and more higher level ADAS, L2, L3, and above for the self-driving vehicles. So the camera model need to be ASIL on the system level. But to achieve this, we are breaking down the model to several small pieces that need to achieve a certain level of safety. And the camera switch is part of these small pieces. So the camera switch need to have the safety capability. And finally, we cannot break the bank. Definitely, we cannot do that. So we are looking for an affordable solution. Let's take case by case. So first one is the scalability. In L2 ADAS, we use 1 to 3 megapixel for the forward-facing camera and the side view camera, and 1 to 2 megapixel for the rear view camera for a total power of 6 to 10 watts. If we look forward for the next step, the L3 ADAS going to need to have higher resolution and more cameras to serve its own purpose. For example, we are moving on the power level by 2x from 6 to 10 watt to 15 to 25 watt. And this is because we're using more cameras, for example, for the surrounding view to have the 360-degree fisheye view. For the rear, we need to have higher resolution, so we are using 5 megapixel cameras with a 2 watt. I would like to have a vehicle that is definitely watching my back. Now the challenge is, how to get smoothly from the L2 to the L3 ADAS system. First, with the current hardware, it's complicated to add more cameras because even the hardware or the software are not fit for this level of scalability. The camera switch itself is not fit for this requirement. In the case of the diagnostics, it's also challenging to change the current sense or the current limitation because it's done through the hardware and it's also managed by the camera switch. This is just one example. Imagine you have an OEM, and this OEM is going to request to change the rear camera. And this rear camera is today, for example, consuming for the L2 ADAS system 1 watt. To the next one that is going to be consuming 2 watts. The current hardware is not allowing that because we are using a resistor as a current limitation. So the OEM is going to formulate a change request. And since the design is done by hardware, the owner of the ADAS, whenever it is OEM, Tier 1 or Tier 2, need to do a new validation and probably a new qualification, which is time consuming. But not only that, it's also money consuming. For the power dissipation, no need to comment, since this is clearly going to be a challenge. Basically, we'll multiply the power by 2, and the dissipation going to be quadratic. And it's absolutely not also in concordance with what we're trying to reach for the software-defined vehicle. Let's push the reflection a little bit more and look for the future L4, L5 ADAS system when we can reach a power in the range of 40 to 60 watts. And this is because of the number of the cameras and the accuracy needed for such system. For example, you're going to need 250-meter range, high definition and high resolution camera for the front, more cameras for the surrounding view, more cameras on the rear, and this is just to cover all the blind spots and to serve a purpose, which is the driving assistance and the self-driving vehicles. So in overall, the scalability is a key factor to aim for when designing the new ADAS system, and the camera switch is one of the subsystems that are important component to look deeper into them. Let's move to this flexibility. Imagine you are a Tier 1 and you need to develop a new ADAS platform. This ADAS platform needs to address the L2 plus, L3 objective, in addition to the new zonal approach that is coupled with the software-defined vehicle. And we need to satisfy some of the requirements. First, the flexible power rating by having the possibility to update the current easily, but also in a fast way. So the SDV need to be somewhere here. Second, the flexible output. For example, an entry-level vehicle need only to have 2 cameras for the surrounding view. And then the mid-level vehicle, it's a full 360 degree with the fish eye view, which going to need definitely 4 cameras and sometimes more. So the hardware platform need to be able to address this, sense this flexibility. To address also the high power rating, we are probably going to need to have multiple IC on the board, which means that we need to interface them. And here, an analog interface on the camera switch is not the best solution because of all the necessary peripherals on the MCU, the ADC, and also all the challenges coming with that, the consumption, the resolution, and everything that is related to that. But sometimes it's just resource. We need to have an interrupt, we need to read it, we need to manage it, and we need to have a lot of work there. And this is why I think and we think that the digital interface is the best solution. So if we have the digital interface with multiple ICs on the board, it also means that we need to have multiple addresses. And this is just one side of the story. What about the adaptation to different OEM topologies? Let's take an example. You have an OEM that is using today your ADAS platform, and he's using 1 megapixel on the left and 2 cameras with 3 megapixel on the right. The same OEM for a mid time update on the vehicle. He would like to change now the 1 megapixel to 3 megapixel, perhaps just for money, perhaps it's just for cost. He can get 3 megapixel. He can buy 4 cameras with 3 megapixel at better pricing. So what's going to be your reaction, even if you have the hardware platform that is not enabling you to do this update quickly, and then you're going to have to do change requests and then all the validation, probably qualification on your side, or you have highly enough flexible hardware that is enabling to do such updates by software, and then it's easy. And from this example, we can extrapolate a lot of use cases where the flexibility is a key factor for the next ADAS architecture. And this is going to have an impact definitely on your development and your IC choices. What about safety? So the goal is to achieve safety level ASIL B, C, or D for the different level of ADAS architectures. So L2, L2 plus, L3, or L4. But we can't restrain the analysis on the component only. We rather reach the ASIL goal on the system level. And on the system, the question that we may ask ourselves is, what information can we provide from the different subsystems to achieve this goal? In general, we can sense voltage, current, temperature, pressure sometimes. And in the case of the camera switch, we talk more about diagnostics and monitoring, which includes the voltage sense of the different outputs, ideally in an independent way, the input voltage, monitoring, the internal VDD, the output current monitoring, and also ideally in an independent way, and the reference voltage, the internal reference voltage. Sometimes the clock, sometimes if we have a digital or an analog interface, we would like to know that the information going in and back is also correct. We may also have some internal ABIS, some internal diagnostics, just to be more helpful and to help the system to reach this ASIL in an easier way. In fact, if we are able to provide all this information, so the voltage, the current, the temperature, internal diagnostic of the IC, the safety goal and analysis can be achieved in a much easier way compared, of course, to the systems where these informations are not available. Now, what's the next step? In fact, at MPS, we have been analyzing all of the above. So the scalability, the flexibility, the safety, just to provide an IC that is able to answer all of those challenges. And on our side, this IC or this solution, it has a name. And this name is the MPQ 5864. It's quad channel or two channels product that is designed for the automotive application such as the ADAS system, and more specifically the cameras. We can also use it for the automotive sensor fusion, for the POC distribution, the power over coax, or just as a system protection. It's coming in a small package, 3x4 QFN17, and in two versions, even ASIL or QM. And this product can support 800 milliamp per channel in the case of the 4 channels, or 1.5 amp per channel in the case of the 2 channels. The accuracy we are also talking about here is plus or minus 3% for 1 amp and plus or minus 5% for 300 milliamp. So it's quite accurate that we can find different use cases, let's say, in our product. Let's have a look at what is under the hood. First, we have two independent input. Each one is supplying two outputs. So for example, in the case of the four channel output or version, we have two inputs for 4 outputs. In the case of the 2 channels, it's 2 input for 2 outputs. It's independent in terms of the channel programmability. For example, the current limit, the channel voltage sense, the thermal sensor. The IC also include internal diagnostics for the band gap, the oscillator. We can configure also the soft start independently for each of those channels. We can have current information in real time or as a peak current mode. And the peak is more used for the DMS as an example. All those information and even more can be communicated and accessible through the I2C. For the safety, we have an analog fault pin that can be used as an indicator in case, for example, we lose the I2C communication in a limp home use case. And for the ADAS, always, we are having internally redundant band gap, a clock error detection, we have a cyclic redundancy check, CRC, we have multiple pins for the V-in and the ground. So in case we lose one of the V-in pins, we do not lose the power on the IC. And also the same case for the ground. Let's see how we can make use of all these functions by exploring different use cases. First one I would like to go through is the most common one, which is the source circuit use case. Here we have two cameras, for example, in the front, connected to the same camera switch and supplied by two independent VIN. Now we have a short circuit between VIN1 and the ground. What's going to happen? We're going to lose this output for sure. But what we would like to do is to control the behavior of the output. We can put it even on auto retry or latch off mode. The channel 2 shouldn't be affected, and this is the case here. So the channel 2 is not affected by default and is completely independent. Third thing, we would like to report. And here's how we report the fault through the fault pin and the I2C. The I2C going to give more in-depth information about the short circuit, and the fault pin going to give more information about there is a fault. And then we need to go deeper to understand it. The second use case that is more related to the first use case, I'm going just to explain in 1 minute why, is about the real-time diagnostics. In fact, inside we have an ADC, 8-bit ADC, that's going to report and provide informations for the output current for each of the output channels in independent way, the output voltage of each of those channels also in an independent way, the input voltage, the internal VDD, and the internal reference voltage. What is important to know is that this ADC can be configured into two modes. The first one is to have a continuous sense and update of different registers. The second one, we can have one-time sample. And you know why? Because when we need to have this, when we need to read some low IQ, this can be very helpful. The third thing, this is what I was saying just before regarding the current sense, is we have the capability to provide the peak current mode for the channels. And this is very, very useful for the driver monitoring system or the DMS. Let's just take a moment before going to the next subject. Imagine you are on this use case, which is the source circuit case, and you are in standby mode. During the standby mode, you don't want it to consume too much. So you can set the I2C to be in one sample time mode. Then you have the short circuits. Then what's going to happen? The product's going, or the IC is going to protect the output, keeping the second channel active. You're going to report through the fault pin. You are in low IQ, so you are in standby. Your microcontroller is also in standby. Then if you have an interrupt here, it's going just to wake it up and tell him, okay, there is a fault, please check. He can come in, ask the IC through the I2C, get the information, and all of this can happen during the IQ mode, during the low IQ mode, without any issue. So this is where the one sample time provided by the ADC here is very useful. The third example I would like to go with is the safety. And the safety starts with a customer safety goal. Here, easy. Our goal is not to lose the feed on the camera. And this is related to two sides. The first one is the data, and the second one is the power. On our side as MPS, we're going to focus more on the power. And second thing is this safety goal, it has a nasal level, which is B, can be C or D. But in this case, we just choose B to make it simple. And by definition, how to achieve the ASLP is by having a fit rate that is below 75 fit while looking over the safety goal itself, while achieving the safety goal itself, which is not losing the camera feed. And for MPS, this is a straightforward solution. In fact, we can supply the two outputs by two regulators. We can communicate all the information to the microcontroller. And since the IC, since this, and this is the case, we did choose the MPQ77220 FS, which is the ASIL B version for the two channels. It's already ASIL rated. No need to do any more work. That's it. In fact, a lot of steps of verification and documentation can be omitted because they are already covered by the documentation that MPS can provide. Question from our side is, what if we need to reach higher level ASIL, or if there is higher level ASIL that is required? Then we take the same use case, we take the same system, but this time we are just going to add more monitoring on the VIN, for example. And this monitoring can be done through safety MCU. It can be done through a PMIC, an ASIL B or an ASIL D PMIC that MPS can provide, or can also be done directly by a regulator that is already rated ASIL that also MPS can provide. Furthermore, MPS is enabling the safety by following the ISO 26262 and provided the safety manual that is developed as a safety element out of context, according all the way to the ISO 26262. And those documents going to include the device base fail rate, or the BFR, the functional failure mode, the safety mechanism, the assumption of use, and much more information. All those information are accessible, and we can have them directly on the safety manual. And all, we're just trying to reach a lower effort to go through the functional safety design and the fast time to market. Let's just recap for one moment. We have talked about the short circuit use case. We have talked about the real-time diagnostics. We have talked about the safety. And we did give those different examples that we can again extrapolate for different other use cases. The subject that we didn't treat yet is the power dissipation. And this is going to be the next slide. So at the beginning, I did talk about the power need is going to be doubled, even quadruple, while going toward the L2 plus the L3 systems. And here's an example of is an example between MPS and one of the competition. Again, the purpose here is not to compare the two solutions, but this is just given as a reference. We propose on our side a 180 milliohm, which allow us to drive 800 milliamp with a drop of about 131 millivolt. And as a side note, the 800 milliamp can also drive the night vision cameras. This can be very useful in different use cases. Let's go back just to the power dissipation. In all use cases, we're not going to be driving the same power on all the channels. So first one is 800 milliamp. The three other outputs we are set here, we did set them here to 400 milliamp on each, which resulted in a drop voltage of about 78 millivolt. With the low RDS on, we have a better efficiency than the competition, and we have also better drop voltage, and thus we have the better thermals. Here's what does the thermal look like. At an ambient temperature of 27 degrees, we have a temperature on the case of about 34 degrees. So our delta T is about 7 degrees. It's really not hot. So you can also imagine that we can put the same switch into other harsh environment at 85 degrees, 100 degrees, and this is not going to be an issue, at least for this use case, and also for others. We can provide you much more information for the thermals. Just reach out to us. We'll be really very, very open to help you. Let's recap. First, the solution we are providing is going to answer the scalability problem. And because we have two channels or four channels outputs, and each channel is independent, and each time one equal two outputs for between the input and the output. Second, We have the independent current limit and the diagnostics. Third, or let's say second step is the flexibility. We have the internal independent current sense, the digital interface for the monitoring and the diagnostic through the I2C. Third, we are its ASIL level, so it's ASIL capable through the fault pin and the internal diagnostics of the IC to reach this ASIL level. Third, on the thermal, it's not hot at all with 7 degrees elevation temperature on the product itself at the use case I did present earlier. And all in all, this is going to allow us to reach a better cost on the system level. And the most important thing is we need to think about this on the system. Let me just conclude with some words. So the webinar that we have presented today is highlighting the pivotal shifts from domain to the zonal architecture in the automotive system. And we have been in phases in scalability, flexibility that are really crucial for advancing the ADAS technologies. The MPQ 5864 is one of the products that MPS is proposing as a standout and also as an innovative solution designed to meet all those challenges. That's going we are offering the programmability, the robust diagnostics, the ASIL compliance, and we're also enhancing the efficiency. We invite you to explore further with MPS, of course, and we will really be very happy to support you at any next generation automotive products and products. So we also encourage you to ask as many questions as you want that you may have also about this topic or others related to this, to the zonal approach in general, to the SDV also in general, and to reach out if you would like to have any more information or assistance. Thank you again for joining us, and I look forward to continue this journey together. Heading back to you, Melina.
Thank you very much, Almedi. Great presentation, very interesting insights. As Almedi already said, feel free to ask any questions that you may have in the Q&A button on the bottom of your Zoom webinar interface. You can type in any questions. And also, I wanted to remind you that we're recording this session and we'll send you a link in the next days. And with this link, you will be able to watch today's webinar on demand. And we will also send you a link to the PDF presentation so you can review it. Exactly. So, Wilson, would you like to start with the first question?
Yes, sure thing, sure thing. Thank you, Melina. Thank you, Almedi. So one of the first questions that everyone asks is, what microcontroller do you recommend to interface with this device?
Sorry, I was on mute. In fact, there is no limitation really to use for the microcontroller side. We can use anything that is having I2C, and again, it depends on the use case on your side. For the cameras, there are different SoCs out there that are using our product, and that is really showcasing why our product is serving a purpose.
Great, thank you. Another question that came up was, I believe on one of the slides, there was a diagram with voltage regs and things like this. The market has been hearing about 48-volt architecture. Does that affect the camera switches? And will MPS come out with any versions to support direct from battery?
We have some ongoing investigation to get the 48 volts. We have some products that are in preparation. There are different information coming also from the market that 48 volts can also supply directly the batteries, but this is going to depend a lot on the topologies by different OEMs. You can really think about it like first OEM would like to have the 48 volt directly supplying the battery, supplying the cameras, and others would like to go through more of step down and then having a constant 12 volt, and then they would like to use the same POC. But at least on MPS side, we're basically prepared for those two use cases. We can provide to you today the 5864, that is a POC product supporting up to 18 volts, and we're also preparing the future for the 48 volts.
Okay, thank you. I think this is a follow-up to the microcontroller question. Is there a Sorry. Would it be more flexible for ADAS platforms to actually go with SPI instead of I2C?
Not 100% sure of that.
Okay, no problem.
Not 100% sure of that. Let me just perhaps extrapolate a little bit. Why? The I2C is more robust, let's say like this, than the SPI. And we see that some different customers around the globe that are really preferring to use the I2C also from the EMI perspectives. When we have some BCI, some bulk injection, the I2C seems to be more robust than the SPI. So the I2C in general is really much better in these use cases.
Yes, I agree. And I think it also just depends on the number of IOs that are available for you guys anyways. Okay, no problem, no problem. I think some of the last questions are, how do you seeing, from insights across the market for just next generation ADAS platforms? Where are they going? Are there any things that, we need to pay attention to? Things like this.
Cameras, of course, if I may. So we see that the different ADAS in the system that we're trying to include more and more functions. If we talk only about the cameras today, we may also say that those cameras need to be highly flexible. And we're really going toward the software-defined vehicles also for the ADAS. So the ADAS platform itself need to be able to answer all those requests that's coming from different OEMs. We don't want to really go each time into change requests, new development, new validation, because this is going to take too much time and it's not the best approach. So the next ADAS system, they're going definitely to use more cameras for different reasons, the self-assistance and the lane departure and everything we are doing right now. But we would like them also to be more efficient. And this is why, so in general, the camera switch is important also to consider, but not only that, there is all the peripheral that's coming from that. So this is answering to the flexibility, the scalability, the ASIL, and of course the cost.
Yeah, Mehdi, there's one more question that came up. So I believe this was in regards to the competition slide that you had there. Do you have any relevant designs or reference designs that customers may use in order to replace perhaps this competitor A or competitor B to this MPS solution?
Of course, yeah, of course. So we have different evaluation boards. We have our own graphical user interface that can be used at first for the evaluation, and then we can help you a lot to move from one competition A, B, or C toward our solution. We are really here to help. This is basically what we have been preparing. This is also why we are winning with this product.
Great. Awesome. So I think that might be the last couple of questions. I will leave it maybe one more minute for anyone else to ask any last minute questions. If not, then thank you guys for joining today's session for MPS camera switches. We really appreciate your guys' time. As Milena had mentioned in the beginning, we will have this on our website relatively soon, and we'll provide these slides out soon as well. Any last closing words, Almedi or Milena?
On my side, thank you so much for joining us. Thank you again. Please don't hesitate if you have any questions. We'll really be very happy to help you with your next generation ADAS. And not only that, also different products that you may have.
Also from my side, thank you for attending and stay tuned for future webinars. We have plenty of interesting topics upcoming. So yeah, see you soon, hopefully. Have a good day.
Great. Thank you, everyone. Bye-bye.
Thank you, everyone. Bye-bye.